Good morning, all. Welcome to the lecture of number 3. Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Thank you. Okay. So in last lecture, we have seen some results depending on the definition of primitive root. Okay. Now let us see some examples. Let m and n are any two integers which are greater than 2 and GCD of these two integers m and n is equal to 1, then there is no primitive root, no primitive root modulo m into n. Okay, what is a primitive root? An integer a is said to be a primitive root modulo n if a to the power 5 of n is congruent to 1 modulo n and a to the power k is not congruent to 1 modulo n whenever k is less than 5 of n. Now here we have provided the two integers m and n which are greater than 2, and also we have given that GCD of these two integers will be equal to 1, that is these two integers m and n are relatively prime, and from that we have to prove that there is no primitive root modulo m into n, or there exists no primitive root modulo m into n. That is, if a be any integer, then a to the power 5 of m into n is congruent to 1 modulo n, and 5 of a to the power k is not congruent to 1 modulo m n. This one will be not possible. As here there exists no primitive root, it means if we take any integer which is relatively prime to m into n, then a to the power some h is congruent to 1 modulo n, and this h is less than 5 of m into 5 of m n. Okay, that is we have to prove. Okay. So see its solution. As here we have to prove that there is no primitive root modulo m n, so we will consider one integer a which is a primitive root modulo m n. If possible, suppose that if possible suppose that a is a primitive root modulo m into n. A is a primitive root modulo m n, it means a to the power 5 of m into n is congruent to 1 modulo n, that is a to the power 5 of m into n is congruent to 1 modulo n, sorry, 1 modulo m n, and a to the power k is not congruent to 1 modulo m into n whenever k is lies between 1 to 2, which is less than 5 of m into n. Okay, then only it is possible that a is a primitive root of modulo m n. As we have taken a is a primitive root modulo m n, then a to the power 5 of m into n is congruent to 1 modulo m n, and a to the power k is not congruent to 1 modulo m n whenever k lies between 1 to and which is less than 5 of m n. Okay, now as a is a primitive root modulo m n, which implies a has order phi of mn modulo mn. Since what is the order of an integer modulo n? That is, if a be any integer which is relatively prime to n, then we have to find out the smallest positive integer k such that a to the power k is congruent to 1 modulo n. Then we say that k is a order of that integer modulo over modulo n. Okay, now as here a to the power 5 of m into n is congruent to 1 modulo mn, and a to the power k is not congruent to 1 modulo mn whenever k is less than 5 of mn, then the integer a has order 5 of mn modulo mn. Okay, now as a is an integer which is a primitive root of mn, which implies as a is a primitive root which implies GCD of a comma mn must be equal to 1. Again, we know that for any three integers a, b, c, GCD of a comma bc will be equal to 1 if and only if GCD of ab is 1 and GCD of ac is 1. As here GCD of a comma mn is equal to 1, which implies GCD of am is equal to 1 and GCD of an is also 1. Now, what is Euler's phi theorem? Euler's theorem. What is Euler's theorem? If n greater than 1 be any, sorry, n greater equal by 1 be any integer and a be any integer which is relatively prime to n, then आवाज येते ना माझा?
Yes, sir.
हा, युलर्स थेरम काय होता? ए एन हा ग्रेटर इक्वल बाय 1 कोणताही एक इंटिजर घेतला आणि ए हा असा इंटिजर घेतला जो की रिलेटिव्हली प्राइम आहे एन सोबत, तर युलर्स फाय थेरम काय सांगत होता?
A raised to phi of m congruent to 1 mod n.
1 modulo n na, as a GCD of am equal to 1, that is integer a is relatively prime to m, then by Euler's theorem, e to the power phi of m, e to the power phi of m is congruent to 1 modulo m, and e to the power phi of n is also congruent to 1 modulo n, since which is from the Euler's theorem. Since as here integer a is relatively prime to both the integers m and n are integers which are greater than 2, then by Euler's theorem a to the power phi of m is congruent to 1 modulo m and a to the power phi of n is congruent to 1 modulo m. Let us take this one as some start. Okay, now let us define one term h, which as h is an integer which is nothing but phi of m into phi of n divided by GCD of phi of m comma phi of n, m comma phi of n. Okay, so here we have defined one integer h which is nothing but phi of m into phi of n divided by GCD of phi of m comma phi of n. Take this one as equation 1. Now we know that the integers m and n are greater than 2. We know that the integers m and n are greater than 2. Then as m and n are integers which are greater than 2, then what is the phi value of m and n? I think we have proved one result. If n is an integer which is greater than 2, then phi of n is always
Even.
what? If n is an integer which is greater than 2, then phi of n is equal to आठवतंय का? n, if n greater than 2 is any integer, then
Even असते सर.
phi of n is always even, असं प्रूव्ह केलं होतं ना आपण. Okay, now as here m and n are two integers greater than 2, then which implies phi of m and phi of n is always even. Phi of n is always even. Okay, now as phi of m and phi of n is always even, then what is the GCD of phi of m and phi of n?
2.
GCD of always 2 येईल का? हो,
Greater than or equal.
ग्रेटर इक्वल बाय 2 येईल, कारण कमीत कमी मला एक तरी फॅक्टर दोघांमध्ये कॉमन मिळेल, कारण m आणि n माझे दोन इंटिजर आहेत जे की ग्रेटर दॅन 2 आहेत. आणि जर ग्रेटर दॅन 2 असेल तर phi of n आणि phi of n हा ऑलवेज इव्हन येतो. ऑलवेज इव्हन येतो याचा अर्थ कमीत कमी एक वेळा तरी मला त्याला 2 हा डिवायझर मिळेल, म्हणजे दोघांमधून 2 ऍटलिस्ट एकदा तरी कॉमन मिळेल, म्हणजे माझा जीसीडी 2 किंवा 2 पेक्षा मोठा असेल.
Yes, sir.
Okay, so GCD of phi of m comma phi of n is always greater equal by 2, since m and n are greater than 2, and as m and n are greater than 2, phi of m and phi of n is always even. Okay, now as GCD of phi of m comma phi of n is greater equal by 2, within the term h is nothing but as h we have defined phi of m into phi of n divided by GCD of phi m comma phi m. Okay, now as GCD of phi of m comma phi of n is greater equal by 2, then what is the relation between this term and this term? Phi of m into phi of n divided by 2. Okay, GCD of phi of m comma phi of n is always greater equal by 2, then what is the relation between these two terms? That is phi of m into phi of n divided by GCD of phi of m comma phi of n and phi of m into phi of n divided by 2. Which one will
Less
be always
equal.
greater equal? This phi of m into phi of n divided by GCD of phi of m into phi of n is less equal by phi of m into phi of n divided by 2. Since GCD of phi of m comma phi of n is greater equal by 2, if it is equal to 2, then these two terms are equal, and if it is strictly greater than 2, then this term is less than this one. Okay, so h is less equal by phi of m into phi of n divided by 2. But we know that Euler's phi function is a multiplicative function. Therefore, as m and n are integers greater than 2 and relatively prime, therefore it can be written as phi of m into n divided by 2, since phi is multiplicative. Okay, so here we get h is less equal by phi of m into n divided by 2. Then phi of m into n divided by 2 and phi of n. What is the relation between these two terms? Phi of mn divided by 2 and phi of mn.
Less equal.
Less equal or strictly less than?
Strictly
phi
less
of m
than.
into n हा स्ट्रिक्टली लहान असेल ना, phi of m into n याला 2 ने डिवाइड करणार तुम्ही जे काही असेल त्याच्यापेक्षा phi of m into n हा ऑलवेज मोठा येईल. हो का नाही?
Yes, sir.
Yes, sir.
ओके, phi of m काहीतरी k असेल, जर त्याला 2 ने डिवाइड केला तर तुम्ही k by 2 ऑलवेज लहान येईल ना त्याच्यापेक्षा. Okay, so here we get h is less than phi of m into n. Let us take this one as equation 2. Now consider, so here we get one integer h which is less than, strictly less than phi of m into n. Now consider a to the power h. A to the power h can be written as, h is nothing but phi of m into phi of n divided by GCD of phi of m comma phi of n. Phi of m comma phi of n. Therefore, it can be written as a to the power some phi of m to the power phi of n divided by GCD of phi of m comma phi of n. Okay, so finally this is nothing but a to the power phi of m into phi of n divided by GCD of phi of m comma phi of n. Okay, now but from equation start, this start a to the power phi of m is congruent to 1 modulo m, which implies this will be congruent to 1 to the power, since a to the power phi of m is congruent to 1 modulo m, 1 to the power phi of n divided by GCD of phi of m comma phi of n modulo m, since a to the power phi of m is congruent to 1 modulo m, which is from start. Okay, so which implies a to the power h is congruent to 1 to the power any integer will be again 1, which is congruent to 1 modulo m. Take this one as equation 3. Similarly, again consider a to the power h, which is nothing but a to the power h again, which is nothing but phi of m into phi of n divided by GCD of phi m comma phi m, and which is nothing but a to the power phi of n to the power phi of m divided by GCD of phi m comma phi m. Okay, again we know that from equation start a to the power phi of n is congruent to 1 modulo n, therefore it is congruent to 1 modulo n, since a to the power phi of n is congruent to 1 modulo n, which is again by star. Okay, so which implies e to the power h is congruent to 1 modulo n. Take this one as equation 4. Now equation 3 says that a to the power h is congruent to 1 modulo m, and equation 4 says that e to the power h is congruent to 1 modulo n, which implies from equation 3 and 4, from equation 3 and 4. Equation 3 is nothing but a to the power h is congruent to 1 modulo m. Then by the definition of congruence, a is congruent to b modulo n whenever n divides the difference of two integers a and b, which implies m divides e to the power h minus 1 h minus 1, and from equation 4 n divides e to the power h minus 1. But we have given that the integers m and n are relatively prime integers, and we know one property: if a is an integer which is relatively prime to both b and sorry a is an a and b are two integers which are relatively prime, and a divides c and b divides c, then a into b must divide c. As here m divides e to the power h minus 1, n divides e to the power h minus 1, and mn are relatively prime, which implies m into n also divides a to the power h minus 1. Now again we have to use the definition of congruence, as mn divides a to the power h minus 1, which implies a to the power h is congruent to 1 modulo mn. Okay, now as a to the power h is congruent to 1 modulo mn, then what is the order of a modulo mn?
H.
Which implies h is the order of a modulo mn. Now, whether this one will be possible, since a is an integer which is primitive root of mn, which implies a to the power, sorry, a has order phi of mn modulo mn, but here we get one integer h which is less than phi of mn, and which is the order of a modulo mn. Whether it will be possible when a is a primitive root modulo mn.
No, sir.
Okay, so this one is not possible. This is not possible since a is a primitive root modulo mn. Primitive root modulo mn. That is, a has order phi of mn modulo mn. But here we get one integer h which is less than phi of mn, and which is the order of a modulo mn. But this is a contradiction to our assumption, and this contradiction arises due to our wrong assumption, that is a is a primitive root modulo mn. As a is a primitive root modulo mn is a wrong assumption, then what will be a correct statement? The integer a is not a primitive root modulo mn. That is, there is no integer which is a primitive root modulo mn. And from as we have proved this one, the integer m into n has no primitive root. Okay, which implies a is not a primitive root modulo mn, and hence from this we conclude that there exists no primitive root modulo mn. Exists no primitive root modulo mn. Okay, and that is we have to prove, and here is the proof. And hence, if m and n are two integers which are greater than 2 and which are relatively prime, then there exists no primitive root modulo mn. That is the product of these two integers m and n. Okay, any doubt?
No, sir.
Okay, if there is no doubt, then we will see the next result. Let p is an odd prime, then there exists a primitive root exists a primitive root r of p such that r to the power p minus 1 is not congruent to 1 modulo p square. Okay, so here we have given p is an odd prime having one primitive root some r. Then we have to prove that r to the power p minus 1 is not congruent to 1 modulo p square. That is, we have to prove the existence of such a primitive root r such that r to the power p minus 1 is not congruent to 1 modulo p square. See its solution or proof. Okay, let p is an odd prime. Let P is an odd prime. Okay, now as P is an odd prime and let one minute. Okay, and let R is a primitive root of P. Okay, as R is a primitive root of P, which implies R to the power 5 of P is congruent to 1 modulo P, and R to the power K is not congruent to 1 modulo P when your K is less than 5 of P. Okay, now we have to prove that R to the power P minus 1 is not congruent to 1 modulo P square. If possible, suppose that this R, for this R to the power P minus 1 is not congruent to 1 modulo P square, then our proof will over here. But if suppose for this integer R to the power P minus 1 is congruent to 1 modulo P square, then we have to find out one primitive root for P such that for that R to the power P minus 1 is not congruent to 1 modulo P square. Okay, so now if R to the power P minus 1 is not congruent to 1 modulo P square, then the proof is complete. Then the proof is complete. Okay, काय करायचंय, फक्त एक ऑड प्राइम मला पी दिलेला आहे, त्याच्यासाठी मला एक असा पीचा प्रिमिटिव्ह रूट शोधायचा आहे की ज्यासाठी आर टू दी पॉवर पी मायनस 1 हा माझा कॉंग्रुएंट नाही आला पाहिजे 1 मॉड्युलो पी स्क्वेअरला. जर समजा मी एक आर हा प्रिमिटिव्ह रूट घेतला, जर तो स्वतःच त्या प्रिमिटिव्ह रूटसाठीच जर आर टू दी पॉवर पी मायनस 1 हा कॉंग्रुएंट येतच नसेल 1 मॉड्युलो पी स्क्वेअरला, तर माझा प्रूफ इथं संपतो. पण जर समजा मी आर हा प्रिमिटिव्ह रूट घेतला पीचा, पण आर टू दी पॉवर पी मायनस 1 हा माझा कॉंग्रुएंट येत आहे 1 मॉड्युलो पी स्क्वेअरला. इफ suppose r to the power p minus 1 is congruent to 1 modulo p square. Okay, actually here we have to find out one primitive root of r of p such that r to the power p minus 1 is not congruent to 1 modulo p square. But here we get one primitive root r, which is a primitive root of p, but r to the power p minus 1 is congruent to 1 modulo p square. But for that case, we have to find out one another primitive root r1 of p such that r1 to the power p minus 1 is not congruent to 1 modulo p square. Then our existence part will be proved, since actually here we have to prove the existence of such a primitive root. Okay, so here we get one primitive root r which is congruent to 1 modulo p square. Then as r is a primitive root of p, r plus p is also a primitive root of p. So primitive root of p. Since over p, what is the value of r plus p? r माझा प्रिमिटिव्ह रूट आहे p चा. मग ओव्हर मॉड्युलो p वर r प्लस p ची व्हॅल्यू काय असेल?
p plus 1.
प्लस 1 कसं असेल? r प्लस p, p ची व्हॅल्यू काय असेल ओव्हर मॉड्युलो p? p ने p ला डिवाइड केला, रिमाइंडर काय राहील?
0.
0 राहील ना, म्हणजे हा r प्लस 0 राहिला शेवटी, म्हणजे टोटल माझा rच आहे का ओव्हर मॉड्युलो p?
Yes, sir.
And as r is a primitive root, then this r plus p is also a primitive root, since r plus p is nothing but the r over p. Okay, so as r is a primitive root, then r plus p is also a primitive root. So replace r by r plus p, that is r1, r by r1, where r1 is nothing but r plus p. Okay, now consider r1 to the power p minus 1. Okay, so which is nothing but r1 is nothing but r plus p, r plus p to the power p minus 1. Okay, now tell me this binomial coefficient r plus p to the power p minus 1 is nothing but, suppose we have to find out x plus y to the power n, then by binomial coefficient it is nothing but summation k running from 0 to n, n c k x to the power n minus k and y to the power k, which is from the binomial coefficient. Okay, since if n is any positive integer. Okay, so x plus y to the power n is nothing but summation k running from 0 to n, n c k x to the power n minus k y raised to k. That is actually, this is nothing but k is running from 0 to n, which is nothing but n c0 x to the power n minus 0, which is n, y to the power 0, k, since k will be equal to 0 for first term, which is y to the power 0 1 plus n c1 x to the power n minus 1 y to the power 1 plus next term n c2 x to the power n minus 2 y square plus up to so on. What should be the last term? Summation k running from 0 to n, which is last term is n cn x to the power n minus n, which is 0, y to the power k, which is n. This will be 0 to the power n. So now, which is finally nothing but n c0. What is n c0? n c0 is nothing but n factorial divided by n minus 0 factorial into 0 factorial. And as 0 factorial will be equal to 1, then n factorial divided by n minus 0 factorial. That is n factorial divided by n factorial. What is its value? N factorial divided by n factorial?
1.
1 plus nc1. nc1 is nothing but n factorial divided by n minus 1 factorial into 1 factorial, which is 1 into x to the power n minus 1 into y plus nc2, which is nothing but n factorial divided by n minus 2 factorial into 2 factorial into x to the power n minus 2 into y square plus up to so on. Last term ncn, again ncn is nothing but n factorial divided by n minus n factorial into n factorial, that is n factorial divided by 0 factorial into n factorial. Again n factorial gets cancelled and 0 factorial will be equal to 1. Therefore again it is 1 into x to the power 0 into y raised to n, that is y raised to n. Therefore in this way we get x plus y raised to n is nothing but 1 plus, actually n factorial divided by n minus 1 factorial can be written as 1 plus n factorial divided by n minus 1 factorial. N factorial can be written as n into n minus 1 factorial. N minus 1 factorial, n minus 1 factorial get cancelled, and which is nothing but n into x to the power n minus 1 into y plus n factorial. Sorry, this n factorial can be written as n minus n into n minus 1 into n minus 2 factorial. N minus 2 factorial, n minus 2 factorial get cancelled. It is nothing but n into n minus 1. 2 factorial will be 2 into x to the power n minus 2 y square plus up to so on last y raised to n as it is. Therefore x plus y raised to n is nothing but 1 plus n into x raised to n minus 1 into y plus n into n minus 1 upon 2 x raised to n minus 2 into y square plus up to so on plus y raised to n. From this one, actually we have to find out the r plus p to the power p minus 1. Now tell me this one, what is r plus p to the power p minus 1? First term will be, sorry, first term I think x raised to n, na? Where is 1 into x raised to n? 1 into x raised to n is nothing but x raised to n. So what is r plus p to the power p minus 1? त्याच्यावरून सांगा हो. x plus y raised to n. What is first term is x raised to n. त्याच्यानुसार इथं काय आहे?
R raised to n.
R raised to p minus 1.
x म्हणजे तुमचा r आहे, p म्हणजे y आहे, मग काय येईल? r to the power
P minus
1.
1.
p minus 1 plus second term n is nothing but p minus 1. p minus 1 into x is nothing but r to the power n minus 1
minus 2.
p minus 2 into y is p plus n is nothing but p minus 1 p minus 1 into p minus 1 minus 1, which is p minus 2, divided by 2. X raised to, here x is r, to the power n minus 2. P minus 1 minus 2, p minus 3. Y square. Y is p square, plus up to so on. What should be the last term? Y to the power n, that is p to the power p minus 1. Okay, so it is actually nothing but r to the power p minus 1 plus p into p minus 1, r to the power p minus 2 plus p minus 1 into p minus 2 in divided by 2, r to the power p minus 3 into p square plus up to so on p to the power p minus 1. Now, over modulo p square. Okay, this r to the power p minus 1 as it is, plus this can be written as p square into r to the power p minus 2 plus, sorry, minus p into r to the power p minus 2, minus p into r to the power p minus 2 plus over modulo p square. What is it, the value of this term? P minus 1 into p minus 2 divided by 2 into r to the power p minus 3 into p square. As p square divides this p square, then what is the remainder when this term is divisible by p square? ओव्हर मॉड्युलो पी स्क्वेअर याची व्हॅल्यू काय येईल? काय असेल व्हॅल्यू ओव्हर मॉड्युलो पी स्क्वेअर? पी स्क्वेअर याला डिवाइड करतो, याचा पूर्णपणे डिवाइड करतो याला, तर ओव्हर मॉड्युलो पी स्क्वेअर रिमाइंडर काय राहील माझा?
p minus 1 into p minus 2.
इंटू आहे हो हे, p minus 1 into p minus 2 divided by 2 into r to the power p minus 3 into p square. p square ला जर हा डिवाइड करत असेल तर या पूर्ण टर्मला डिवाइड करतो ना p square.
Yes, sir.
मग रिमाइंडर काय राहील? बी इंटू सी आहे माझं. बी इंटू सी मध्ये माझं ए डिवाइड करते बी ला, तर ए जर बीसी ला जर डिवाइड करत असेल तर रिमाइंडर काय राहील?
0.
0 राहील ना. म्हणजे याची व्हॅल्यू काय येईल? माझी 0 येईल. पुढच्या टर्म मध्ये माझं इथं कोएफिशियंट काय मिळेल ते मिळेल, पी मायनस 1 इंटू पी मायनस 2 इंटू पी मायनस 3 डिवाइडेड बाय 3 फॅक्टोरियल इंटू आर टू दी पॉवर पी मायनस 4 इंटू पी क्यूब राहील. परत पी क्यूबला पी स्क्वेअर डिवाइड करेल,
Yes, sir.
तिथं रिमाइंडर परत माझा 0 मिळेल. म्हणजे असं शेवटपर्यंत माझा परत पी टू दी पॉवर पी मायनस 1 ला परत पी स्क्वेअर डिवाइड करेल आणि शेवट ही रिमाइंडर माझा 0 राहील. परत इथे एक टर्म राहिली पी स्क्वेअर, याला सुद्धा माझं टर्म पी स्क्वेअर डिवाइड करेल, म्हणजे याची व्हॅल्यू 0च आहे. म्हणजे ओव्हर मॉड्युलो पी स्क्वेअर ही टर्म काय येईल? आर टू दी पॉवर पी मायनस 1 मायनस ऑफ पी इंटू आर टू दी पॉवर पी मायनस 2 ओव्हर मॉड्युलो पी स्क्वेअर, सिन्स इट्स व्हॅल्यू इज अगेन 0. सो आर प्लस पी टू दी पॉवर पी मायनस 1 is nothing but r to the power p minus 1 minus of p into r to the power p minus 2 modulo p square. Okay. Total our conjugation here, which is nothing but r1 to the power p minus 1 is congruent to 2, r to the power p minus 1 minus of p into r to the power p minus 2 modulo p square. Okay, but here we have considered r to the power p minus 1 is congruent to 1 modulo p square, which implies this one is nothing but 1 minus p into r to the power p minus 2 modulo p square. Now here we have to prove that this r1 to the power p minus 1 is not congruent to 1 modulo p square, and r1 to the power p minus 1 is congruent to 1 modulo p square whenever p into r to the power p minus 2 is congruent to 0 modulo p square. Then only it is possible that r1 to the power p minus 1 is congruent to 1 modulo p square. Now check whether p into r to the power p minus 2 is congruent to 0 modulo p square, whether this one will be possible. As here r is a primitive root of p, then what is the GCD of r and p?
1.
1. As r is a primitive root, which implies GCD of r and p is equal to 1. As GCD of r and p is equal to 1, which implies p does not divide r to the power p minus 1. Since GCD of r and p is equal to 1, that is p does not divide r to the power p minus 2 also. Okay, so as p does not divide r to the power p minus 2, which implies there ह्या आर मधून आर टू दी पॉवर पी मायनस टू मधून मला कधीही पी हा कॉमन मिळणार नाही. याचा अर्थ ही टर्म कधी झिरो होणं पॉसिबल आहे का? ही टर्म
No,
माझी
sir.
ओव्हर मॉड्युलो पी स्क्वेअर झिरो कधी होईल? जर एक पी माझ्याकडे ऑलरेडी आहे. जर ह्या आर टू दी पॉवर पी मायनस टू मधून एखादा पी जर मला कॉमन मिळत असेल तरी त्यात पी स्क्वेअर येईल आणि ओव्हर मॉड्युलो पी स्क्वेअर याची व्हॅल्यू झिरो होईल तेव्हा. पण जीसीडी ऍज आर इज अ प्रिमिटिव्ह रूट, जीसीडी ऑफ आर कॉमा पी इक्वल टू 1, दॅट इज देयर इज नो p factor in this r to the power p minus 2. Therefore, p into r to the power p minus 2 is not congruent to 0 modulo p square. As p into r to the power p minus 2 is not congruent to 0 modulo p square, then r1 to the power p minus 1 is never congruent to 1 modulo p square. Since p into r to the power p minus 2 is not congruent to 0 modulo p square, as p into r to the power p minus 2 is not congruent to 0 modulo p square, then this will be not congruent to 1 modulo p square. That is r1 to the power p minus 1 is not congruent to 1 modulo p square, which implies r1 to the power p minus 1 is not congruent to 1 modulo p square, where r1 is nothing but r plus p. Actually, here we have to prove the existence of such a primitive root. So we have taken one primitive root r of p such that if r to the power p minus 1 is not congruent to 1 modulo p square, then the proof will be over at this step only. But if possible, we have supposed that r to the power p minus 1 is congruent to 1 modulo p square. Then we have find out one more primitive root r1 of p such that r1 is nothing but r plus p. But over modulo p, this r plus p is nothing but r, and r is a primitive root, which implies r1 is again a primitive root of p. And from that we have considered r1 to the power p minus 1, and r1 to the power p minus 1 is nothing but r to the power p minus 1 minus of p into r to the power p minus 2 modulo p square. But as r is a primitive root, gcd of r and p is equal to 1. As gcd of r and p is equal to 1, then there is no p factor in this r to the power p minus 2. Therefore, p into r to the power p minus 2 is never congruent to 0 modulo p square. Therefore, r1 to the power p minus 1 is never congruent to 1 modulo p square. Therefore, if r is a primitive root of p such that r to the power p minus 1 is congruent to 1 modulo p square, that case we get one more primitive root r1 of p such that r1 to the power p minus 1 is not congruent to 1 modulo p square. Therefore, always such a existence of such a primitive root will be possible such that r1 to the power p minus 1 is not congruent to 1 modulo p square, and hence the proof. Okay, कुणाला काही डाऊट यामध्ये? काय करायचं होतं, माझ्याकडे एक ऑड प्राइम होता पी. त्यासाठी मला हे एक्झिस्टन्स दाखवायचं होतं की त्याला एक प्रिमिटिव्ह रूट आर हा मिळतो, ज्यासाठी की r टू दी पॉवर p मायनस 1 हा माझा कॉन्ग्रुएंट येत नाहीये 1 मॉड्युलो p स्क्वेअरला. त्यासाठी आपण एक प्रिमिटिव्ह ऑड प्राइम p दिलेला आहे, एक प्रिमिटिव्ह रूट घेतला r. त्यासाठी जर समजा r टू दी पॉवर p मायनस 1 हा कॉन्ग्रुएंट येत नसेल 1 मॉड्युलो p स्क्वेअरला, तर माझा प्रूफ तिथंच संपतो. पण इन केस समजा माझा r हा प्रिमिटिव्ह रूट आहे p चा, पण r टू दी पॉवर p मायनस 1 हा कॉन्ग्रुएंट येत आहे 1 मॉड्युलो p स्क्वेअरला, तर त्या केससाठी मला एक प्रिमिटिव्ह रूट दाखवावा लागेल p साठी, जो ज्याची पॉवर घेतल्यानंतर, ज्याची पॉवर p टू दी पॉवर p मायनस 1 घेतल्यानंतर तो कॉन्ग्रुएंट नाही यायला पाहिजे 1 मॉड्युलो p स्क्वेअरला. म्हणून इथं इफ पॉसिबल वी हॅव कन्सिडर्ड r टू दी पॉवर p मायनस 1 is congruent r1 equal to r plus p, as r is a primitive root and over modulo p r plus p is nothing but r, then r1 is also a primitive root. Therefore, here we get one primitive root r1 of p. From that we have considered r1 to the power p minus 1, but r1 to the power p minus 1 is nothing but r to the power p minus 1 minus of p into r to the power p minus 2. But r to the power p minus 1 is congruent to 1 modulo p square. That is, in case 2 we have assumed that r to the power p minus 1 is congruent to 1 modulo p square. मग हा कॉन्ग्रुएंट झाला माझा 1 मॉड्युलो p स्क्वेअरला, पण r हा प्रिमिटिव्ह रूट असल्यामुळे जीसीडी ऑफ p and r equal to 1. Therefore, there is no p factor in this r to the power p minus 2. Therefore, this will be never congruent to 0 modulo p square. Hence, r1 to the power p minus 1 is not congruent to 1 modulo p square. Okay. तुला काही डाऊट यामध्ये?
No, sir.
नक्की ना? फक्त एक्झिस्टन्स दाखवायचा आहे मला प्रिमिटिव्ह रूटचा तसा, आणि तो ऑलवेज मिळतो मला. r1 डिफाईन केल्यानंतर तो मिळाला, कारण r टू दी पॉवर p मायनस 1 जर कॉन्ग्रुएंट नसेल तर काहीच प्रॉब्लेम नाही. पण तो जर असेल तर तुम्ही एक r1 डिफाईन करू शकता, ज्यासाठी r1 माझा r प्लस p असेल आणि r1 टू दी पॉवर p मायनस 1 इज नॉट कॉन्ग्रुएंट टू 1 मॉड्युलो p स्क्वेअर येईल. कधी येईल हे? जर r टू दी पॉवर p मायनस 1 हा कॉन्ग्रुएंट असेल 1 मॉड्युलो p स्क्वेअरला. तर जर r टू दी पॉवर p मायनस 1 जर कॉन्ग्रुएंट नसेल 1 मॉड्युलो p स्क्वेअरला, तर त्या पहिल्या स्टेप मध्ये माझा प्रूफ संपतो. ठीक आहे?
Yes, sir.
ओके. Next result. The integer small n fails to have a primitive root, have a primitive root if either first one n can be expressed as a product of two distinct order primes. Two distinct odd primes, or second, n is of the form n is of the form 2 raised to m into p raised to k, where p is an odd prime and m is greater than 2. Okay, so here we have to prove that the integer small n fails to have a primitive root. That is, the integer n has no primitive root if n is of the form product of two distinct odd prime, that is p and q are two distinct primes and n is nothing but p into q. जर त्या फॉर्म मध्ये असेल तरी n ला प्रिमिटिव्ह रूट नाही हे प्रूव्ह करायचं आहे, किंवा जर n हा या फॉर्म मध्ये असेल 2 raised to m into p raised to k where p is an odd prime, then also n has no primitive root modulo n. That is we have to prove. See the proof. We'll take the first case, that is n can be expressed as a product of two distinct odd primes. Let p and q be two distinct odd primes, such that n is equal to p into q. That is, n can be expressed as a product of two odd distinct primes. So here n is nothing but p into q. As p and q are two distinct odd primes, then p and q must be greater than 2, which implies p comma q are greater than 2, since the first odd prime is nothing but 3, which is greater than 2, and p and q are two distinct odd primes, then p and q must be greater than 2. And as p and q are two distinct odd primes, then what is the GCD of p and q?
1.
GCD of p and q will be equal to 1. Therefore, here we get two integers in. Previously we have proved one result. If m and n are two integers which are greater than 2 and GCD of these two integers will be equal to 1, then there is no primitive root modulo mn. Okay, now as here p and q are two integers which are greater than 2 and which are relatively prime to each other, then by previous result, there exists no primitive root modulo p into q. That is, p into q is nothing but n. That is, there is no primitive root modulo n, since n is nothing but p into q. Therefore, for first case the result will be proved, since if n is a product of two distinct odd primes, then there is no primitive root modulo n. Okay, so first will be proved. Now second case, let n is equal to 2 raised to m into p raised to k. Okay, but as 2 is an even integer and p is an odd prime, then what is the GCD of 2 raised to m comma p raised to k?
1.
Again 1. P is odd prime, which implies the GCD of 2 raised to m comma p raised to k is equal to 1. And also we have provided m is greater than 2. As m is greater than 2, which implies 2 raised to m is also greater than 2. And p is an odd prime and k is an integer which is greater than 1, which implies p raised to k is also greater than 2. Since p is an odd prime, p is an odd prime, it means it is starting from 3. Therefore 3 raised to any positive integer must be greater than 2, which implies 2 raised to m and p raised to k are greater than 2. And gcd of 2 raised to m comma p raised to k is equal to 1, which implies again by previous result, here we get two integers 2 raised to m and p raised to k which are greater than 2 and which are relatively prime to each other. Again by that result, there is no primitive root, there is no primitive root modulo 2 raised to m into p raised to k. That is, there is no primitive root, no primitive root modulo n, since n is nothing but 2 raised to m into p raised to k. Therefore for that case also we have proved there is no primitive root modulo n, hence the required result. Okay, so in both the cases, if n is of the form p into q where p and q are two distinct odd primes, then also the integer n has no primitive root. And if n equal to 2 raised to m into p raised to k where p is an odd prime, then also we get n has a no primitive root modulo n, that is 2 raised to m into p raised to k. Here's the required result. Okay, any doubt?
No, sir.
Okay, now there is one note. Let small n be an integer, n be an integer possessing primitive root and GCD of an is equal to 1, then the congruence x to the power k congruent to a modulo n has a solution if and only if a to the power phi of n divided by d is congruent to 1 modulo n, where d is the GCD of k comma phi of n. Okay, and if it has a solution, then there are exactly d solutions modulo n. Okay, so this will be a result which can be used to solve some problems. Okay, so let here we have given one integer n which possesses a primitive root. It means it has a some primitive root r, and a be any integer which is relatively prime to n. Then the congruence of the form x to the power k congruent to a modulo n has a solution if and only a to the power phi of n upon d is congruent to 1 modulo d, sorry 1 modulo n, whenever d is nothing but the GCD of this k and phi of n. And if it has a solution, then there are exactly d solutions modulo n. If there is no solution, then there is no problem. But if it has a solution, then they are d in number. Okay, now if suppose instead of n, if we take p be any prime which has a primitive root, then when the congruence x to the power k congruent to a modulo p has a solution, if p is a prime possessing primitive root and GCD of a comma p equal to 1, then the congruence x to the power k congruent to a modulo p has a solution if and only if a to the power phi of n, that is phi of p. What is the value of phi of p?
P minus 1.
P minus 1 upon d congruent to 1 modulo p, where d is nothing but GCD of k comma phi of n. Phi of n is here p minus 1. Okay, so if p is any prime, then how will you check if any integer a is relatively prime to p? Then the congruence x to the power k congruent to a modulo p has a solution if and only if a to the power p minus 1 upon d is congruent to 1 modulo p, where d is the GCD of k comma p minus 1. Okay, so this note will be important. हे लक्षात ठेवा बरं का, प्रॉब्लेम सॉल्व करण्यासाठी यूज होईल. लेट अस टेक वन प्रॉब्लेम. Show that the congruence x to the power 18 congruent to 5 modulo 73 is not solvable. That is, it has a no solution. That is, it has no solution. Okay, now find out its solution. Okay, so here what is the value of n?
73.
73. Whether 73 is a prime?
Yes, sir.
As 73 is prime, then what is the phi of 73?
72.
73 minus 1, which is 72. Okay, now, and what is the value of p here? Sorry, what is the, as 73 is a prime, then in this case n is nothing but p. Okay, now what is the value of k?
18.
18, and a is equal to 5. Now we know that the congruence of the form x to the power k a congruent to a modulo n has a solution if and only if a to the power phi of n upon d is congruent to 1 modulo n. Then we have to consider a to the power phi of n. Okay, so consider a to the power phi of n upon d. Okay, upon d, which is nothing but a is nothing but 5 to the power phi of p, which is 73, divided by d. D is nothing but GCD of, first find out the GCD. D equal to GCD of k comma phi of n, which is equal to GCD of k is nothing but 18, and phi of n will be, that is phi of 73 is 72. What is the GCD of 18 and 72?
18.
18. So d equal to 18. So put the value up here, d, which is nothing but 5 to the power phi to the phi of 73 is 72 divided by 18, which is equal to, now 5 to the power 72 divided by 18, which is 4. Okay, which implies a to the power phi of n upon d is nothing but 5 to the power 4, and which is congruent to which number over modulo 73? 5 to the power 4 is nothing but 5 into 5, 25, 25 into 5, 125, 125 into 5, 625. Okay, now what is the value of 625 over modulo 73? That is, when we divide 625 by 73, then what is the remainder?
Forty-one.
41 modulo 73, which implies 5 to the power 4 is congruent to 41 modulo 73. That is, a to the power phi of n upon d is congruent to 41 modulo 73. Now, from this note, any congruence x to the power k congruent to a modulo n has a solution if and only if a to the power phi of n upon d is congruent to 1 modulo n. But here we get a to the power phi of n upon d is congruent to 41 modulo 73. That is, 5 to the power 4 is not congruent to 1 modulo 73, which implies the congruence x to the power 18 congruent to 5 modulo 73 has no solution. That is, it is not solvable. Not solution means this one is not solvable. Okay, so in this way we can solve the problem. Any doubt?
No, sir.
No, sir.
Okay, take one more example, which is show that the congruence x to the power 15 congruent to 7 modulo 19 is solvable. Okay, now what is the value of n here?
19.
Here n equal to 19, k equal to 15 and a equal to 7. Now phi of n, whether of 19 is a prime,
Yes, sir.
which is nothing but 19 minus 1, which is 18. So phi of n is nothing but 18. So consider a to the power phi of n upon d. First find out d. Let d equal to gcd of k comma phi of n, which is nothing but gcd of k will be 15, phi of n will be 18. What is the gcd of 15 and 18?
3.
3.
3. Okay, so consider e to the power phi of n divided by d, which is nothing but a will be 7 to the power phi of n. Phi of n is 18 divided by d, d is 3. That is 7 to the power 18 divided by 3, 6 over modulo 19, which implies what is the 7 to the power 6? Before going to 7 to the power 6. Late. 7 square is 49. 7 cube is
343.
7 to the power 3 is congruent to 343 modulo 19. What is the value of 343 over modulo 19?
1.
Which is congruent to 1 modulo 19, which implies 7 to the power 6 is congruent to 1 modulo 19. Since here we have to take just value of k will be equal to 2. Therefore, here we get 7 to the power 6 is congruent to 1 modulo 19. That is 8 to the power phi of n upon d is congruent to 1 modulo 19. Then by that note, which implies the congruence x to the power 15 congruent to 7 modulo 19 is solvable or has a solution. Okay, and here is the proof. Okay, कुणाला काही डाऊट यामध्ये?
No, sir.
No, sir.
Okay.